Hello everyone, I am Talha Paracha, a PhD student at Northeastern University. Today I'll present our work about certificate pinning in mobile applications. This work is done with amazing collaborators from a variety of institutes and is co-led by me and Amog. Amog is also a PhD student at Northeastern and will present the second half of this talk. We start with the problem of protecting network traffic from mobile devices. It's an important problem as mobile apps transmit sensitive data over the internet. For example, data sent by social media, banking, or health apps. So, how do apps protect this data? Well, they mainly use TLS, the de facto network security protocol. For the most recent versions of Android and iOS, network traffic is sent over TLS by default. So let's take a closer look at how the protocol works. We have an app trying to establish secure connection with a server. To establish the connection, the app will send a client hello message and the server will respond with a server hello message. These messages are part of what is called a TLS handshake. An important aspect of TLS handshake is certificate validation. That is, at some point during the handshake, the server will send a certificate chain to the app. The certificate chain will contain the certificate of the server. This certificate in turn will contain the cryptographic material that can be used to establish a secure connection with the server. But how does the app trust that the cryptographic material it receives indeed is the one sent by the server and has not been tampered with? Well, as mentioned earlier, the app receives a certificate chain. Each certificate in the chain is signed by the one before it. The top certificate in the chain is called the root certificate, and as long as that is trusted, the app can validate the whole certificate chain. Now, to enable apps to make a decision about whether a root certificate can be trusted or not, modern devices come pre-equipped with a store of these root certificates. This store is provided by the operating system of mobile devices. So as long as the root certificate received by the app matches at least one of the certificates in this OS certificate store, the certificate validation can pass. If all checks go well, a secure communication channel is established between the app and server. So are we done with the problem of protecting mobile network traffic? Turns out there are a couple of issues with trusting OS certificate store. First, the store may contain untrusted certificates. You see, these certificates are managed by organizations called certificate authorities, and for one reason or the other, they might not do their job very well. For example, in the past, a certificate authority has been found to issue rogue certificates for Google servers. This meant that TLS traffic to Google could have been intercepted by attackers. Thus, an app might not want to trust some or all of these certificates in the OS store. Second, the OS certificate store can also be customized by device owners. This can enable greater transparency by allowing owners to inspect the network traffic being sent by apps. On the other hand, this can potentially expose apps' APIs and make them more susceptible to abuse. I'll note that this list is not exhaustive by any means, but only highlights some of the issues with trusting the OS certificate store. So let's take a look again at certificate chain validation. While not a part of the TLS protocol, one way to avoid trusting OS certificate store during the validation process is to use the technique called certificate pinning. In pinning, instead of relying on the OS certificate store, the app itself can provide the certificate that is to be expected during a TLS handshake. Certificate pinning also offers more flexibility, in the sense that the app can pin either a root certificate or a leaf certificate or the hash of the certificate. I'll also note that the certificate can be pinned either by the app or an SDK in the app. This study is about certificate pinning in Android and iOS applications. And now that we understand what pinning is, next question is it worth studying? I would argue it is, because first, it is unclear how prevalent certificate pinning is in the mobile ecosystem. Here we show the pinning prevalences mentioned by prior works. These works are from the past 10 years and the references are from the paper. We can notice that the prevalences vary significantly from as high as 28% to as low as below 1%. In addition, all of these works focus on Android. To the best of our knowledge, certificate pinning on iOS has never been studied before. By comparing across platforms, we can reveal differences in pinning and their implications for security. Second, based on our survey of prior literature, we realized there is a need for platform independent, reliable way to detect pinning. Some prior works have used static analysis techniques that do not scale to other platforms, while others have used dynamic analysis techniques where it is unclear how pinning behavior is distinguished from other confounding factors. Third, we would simply like to know how is pinning implemented. That is, more insights about code that contributes to pinning, whether pinning is done on the leaf, root, or a certificate hash, and the security implications of these decisions. And last, we'd also like to know when is pinning implemented. That is, categories of apps that pin, destinations that are pinned, and the data that gets sent in pin connections. I can now present a high-level overview of the methodology used in our work. The first step was data collection. We crawled apps from official Android and iOS app stores. More specifically, for each platform, we got 1,000 popular and 1,000 random apps. These two datasets can help us understand the prevalence of certificate pinning in different parts of the mobile ecosystem. We also curated a peculiar dataset of apps for which we have both Android and iOS versions available. We call this the common dataset. This dataset can help us understand whether app developers use pinning consistently across different platform versions of their apps. Moving on, we decompile these apps to statically look for signals that may indicate certificate pinning use. We first checked for network configuration files in Android apps, as this technique has been used frequently in the past. While this method only works for Android, rest of our methodology is cross-platform. We then looked for certificates embedded in the apps. We looked for relevant file name extensions as well as any strings with delimiters that correspond to certificates. We also looked for embedded certificate hashes using a custom regex search. When we found these hashes in app contents, we attempted to retrieve full certificates using a certificate search engine that indexes CT logs. The benefit of using static analysis is that it highlights the code and paths that contribute to pinning, which we can do further analysis on. But the main limitation of this method is that it may overestimate pinning prevalence. For example, static analysis may point us to unused or stale code in apps. So to mitigate that, we relied on dynamic analysis to confirm which network connections are pinned in apps. To trigger network traffic from an app, we simply open it and record all traffic sent in the first 30 seconds. In more detail, we triggered network traffic in two distinct settings. First, when app traffic is not intercepted in any way, no matter whether a connection is pinned or not, it will succeed in this setting. But in the second setting, we first install a custom certificate in the OS store. We then intercept the app traffic. Remember that pinned connections do not rely on the OS store, so they will fail in this setting, and that is how we identify them. This description about the process is simplified, so please take a look at our paper for complete details. I'll also note that our methodology has some limitations, like we do not explore complete app functionality, and we detail all those limitations in the paper as well. That is all from my side, and now I'll hand it over to Amok.
Thanks, Talha. I will now be going over our results and findings. We would first like to understand the prevalence of pinning and compare it to prior techniques. I'd like to mention here that when we use the term pinning in the remainder of this talk, we mean pinning found using our dynamic analysis technique. We use a bar chart to understand the prevalence of pinning, where each bar represents prevalence, which is split based on their data sets, and each color of the bar represents the technique used to find pinning. In the table, we represent the same data but in a different format. The rows represent combinations of data set and platform, while columns represent techniques. We'd like to start out with comparing to prior work, and the apples to apples comparison with prior work can only be done for Android. We find that prior work consistently underestimates the prevalence of pinning. The greatest difference is in the popular Android dataset, where we find 6.7% pinning compared to 1.8%. Thus, our work provides a better understanding of the adoption of pinning, which was previously thought to be much lesser. Our findings also suggest that apps likely have many options and not use just configuration files to deploy pinning. An interesting next question here is whether popularity has an effect on pinning. To understand this, let's look at pinning prevalence in the popular and random data sets. Continuing with Android, we see that popular apps pin more frequently than random apps. In fact, this is true for iOS as well, where we see popular apps pinning more than random ones. This indicates that popular apps might care more about improving the security of their network connections and that they use advanced techniques such as certificate pinning to achieve this. Lastly, the common data set is pretty interesting because it provides an apples to apples comparison for cross platform apps. For this set, we see a comparable prevalence of pinning. Although on further investigation, we find that about 40% of apps that pin either on Android or iOS pin on both platforms. We omit further details in this talk, but please take a look at our paper for the different ways we compare apps in the common data set. So basically, we've seen that prior work underestimate the prevalence of pinning among Android apps, and we've also seen the effects of popularity and that popular apps tend to pin more frequently than random apps. Next, let's try to understand the characteristics of apps that deploy pinning. Particularly, we'd like to understand the categories of apps that pin more frequently than others. For each app in our data set, we use category information provided by the app stores that we collect them from. And understanding the differences in pinning adoption between categories will help shed light on why apps might want to use this technique. We combine all three data sets from each platform and look at the overall percentage of apps that pin for each category. On both Android and iOS, we find that financial apps have the highest adoption of pinning. This makes sense as financial apps deal with sensitive banking data and would thus need to have stricter restrictions and deploy certificate pinning. The next apps we have are social apps and events apps for Android and shopping and travel apps for iOS. This makes sense as well as these apps tend to deal with personal data and would thus need to deploy pinning to protect this data. From this analysis, we learn that apps that deal with user personal data prefer to implement certificate pinning more often than apps that don't. As a side note, categories between Android and iOS are not the same, thus making an apples to apples comparison here across platforms infeasible. Having seen the types of apps that deploy pinning, let's look at how exactly pinning is implemented by these apps. More specifically, we would like to understand the nature of PIN certificates and their influence on the other aspects of TLS security, like validation logic and cipher support. The first question that we ask is whether PIN certificates are custom certificates or whether they are present in OS root stores. Root stores tell us that pinning is done solely for security, as without pinning, TLS connections could still be established. Custom certificates, on the other hand, are ambiguous. They could be used either for security or for customizability or for a combination of both. In our study, we find that a vast majority of PIN destinations use OS root certificates. This tells us that developers use pinning primarily for its security guarantees as opposed to customizability. The next question we ask is whether root or leaf certificates are pinned. In terms of security, pinning leaf certificates implies that no compromised root certificate can circumvent the security of a TLS connection. But leaf certificates tend to have shorter validity periods and are thus renewed more often. This in turn means that developers would need to update apps more frequently to handle changing leaves, and outdated apps with old pinned leaves become unusable. This trade-off gives us an intuition as to why a high number of PIN certificates are roots in fact. We see that 70% of apps in our dataset are this way. We now check whether PIN TLS connections offer better security in terms of cipher support in these connections. In general, we see lesser support for V-ciphers in PIN TLS connections as compared to the overall set of connections. Thus, in general, pinning implementations in our dataset tend to improve TLS security. Lastly, we consider TLS expiry checks. If PIN certificates are accepted regardless of expiry, it clearly compromises security as expired certs result in successful TLS connections. But based on our analysis, we find no evidence of expired certs. This tells us that pinning adoption does not undermine other certificate security measures, particularly expiry checks. Summing up, we have just seen that pinning is primarily used for its security implications. We have also seen that in general, pinning implementations tend to improve aspects of TLS security by supporting less bad ciphers and by not accepting expired certificates. Next, we would like to further understand pin traffic characteristics. Particularly, we'd like to know if apps that pin do so for all domains that they contact. Then we'd like to see how apps are related to the domains that they pin and whether they pin first or third parties. Lastly, we'd also like to look at pin traffic itself and see what it may contain. In our study, we found that apps that implement pinning almost always contact multiple hosts. When apps pin, they don't tend to pin all domains. In fact, only 7% apps on Android and 3% on iOS pin all domains that they contact. This tells us that most apps have different levels of security for the various domains that they contact. It could also suggest that pinning might be required for some components of apps while not required for others. This might be due to third party requirements, which brings us to the next question. Are pinned domains first or third parties? We see that across datasets and platforms, a higher percentage of apps pin third parties as opposed to first parties. This is interesting as it provides some insight as to who is responsible for pinning within an app. We also try to use static analysis to correlate these first and third parties to SDKs found in apps, details of which can be found in the paper. Lastly, we circumvent pinning to look for PII behind pinned connections, but find no statistically significant difference between pinned connections and not pinned connections. More details about this as well can be found in the paper. So, in conclusion, we performed the first cross platform study of certificate pinning on mobile apps for both Android and iOS. We present a technique that is platform agnostic that finds pinning among these apps, and we find a higher prevalence of pinning using this technique. We look at various aspects of pinning adoption and find that popular apps are more likely to implement pinning, and that apps dealing with sensitive user data are also more likely to implement pinning. We found that pinning usually improves the security of TLS connections. We also found that a major portion of apps that pin don't pin all domains that they contact, and found no evidence of pin connections being used to collect user data more frequently than regular ones. We thank you for your time and now open the floor for questions.